So in previous videos, we've talked about adding vectors graphically. So we've done things like this. This plus this equals this. Right? So I'm going to introduce a little bit of notation before we do what we're going to do today, which is the reverse. Today we're going to take this vector, which is here, and we're going to break it down into its component parts along the x and y axes. So first thing I want to do is introduce some notation. So most people are familiar with graph notation, which is your standard plot here, where if I have a dot here and this is 1 and this is 1, then this point is 1, 1. So vectors is a very similar notation, where if we have a vector and we call 1, 1, it's the same thing except you draw an arrow to that point from the origin. One question might be, well, how do we know where the origin is? The nice thing about physics is you can really pick your origin wherever you want. If you look outside, you don't see a tree that says 0, 1. So you can make your origin wherever you want, which is easiest to do is just to make your origin at the tail of the vector where it starts. So that's some notation. If you want to, this is called the x component and the y component. So if I have a very general vector, which I'll call A, that will have an x component, which is A sub x, and a y component, A sub y. To add components together, to add vectors, if we want to do this, this vector we know is, actually, we don't need to draw them again. We know this vector is 1, 0. We'll say it's length 1. So we have 1, 0. And we want to add it to this vector, which is 0, 1. So we'll say plus 0, 1. To add vectors together, you just add right across. So this is equal to 1, 1. 1 plus 0 is 1, 0 plus 1 is 1, and indeed that seems right. 1, 0 looks like this, 0, 1 looks like this, 1, 1 should look like that, and indeed it does. So that's how to add vectors using this more mathematical vector notation. So, to break a vector into components, which is what we really want to do, we want to get these two things from this one. And there's going to be reasons for that make themselves apparent when we start talking about forces and motion and things like that. So, let's say I have a vector like this, and this is of length 5, and this angle is 45 degrees, just suppose. So, we want to find the vector components that add to give that vector. And we want the components to be the components that are the x and y components, horizontal and vertical. So we're looking for this vector plus this vector, right? And that's a right triangle. So we can use our right triangle trig. This problem is identical, very close, not identical actually, to this problem. X, y, 5, 45. And we know how to do this. And this is essentially the same. The only thing you have to watch with this is the signs. If we have an arrow that goes down or to the left, we have to remember that that sign is negative, because vectors have direction, not just magnitude. This has just magnitude, this has magnitude and direction. In this case, both our things are positive, so we're all set. So, if I call this vector, we'll call it v, then the length of this side is the y component, so this is vy. The length of this side we'll call vx, x. So we want to solve them. So this is our opposite, 45, our hypotenuse, and our adjacent. So setting this up, we can solve, let's do opposite vy first. So this is our opposite, we have our hypotenuse, we have our angle, so let's use sine. So sine of theta is equal to the opposite over the hypotenuse. So plugging these in, theta is 45 degrees. The opposite is v sub y. And the hypotenuse is 5. So 5, so we have that our y component, vy, is equal to 5 times the sine of 45 degrees. You can go through doing the exact same thing with the vx, which is the adjacent. So here you're going to have cosine of 45 degrees is equal to v sub x over 5, and then v sub x is equal to 5 times the cosine of 45 degrees. And that really is all there is to it. The ability to break vectors into their x and y components it's a very useful thing to be able to do. You can also do other things from trig with these. So if I said, suppose I have these two components, 2, 1 plus 1, 1, and this equals 3, 2. Suppose I want to know what the angle of that vector is. So 3, 2 might 1, 2, 3, 1, 2 might look something like that. So if we want to find this angle, theta, well, we know the components. We know this is 3 and this is 2. Right? So from there we can just use our inverse trig functions. And we can say, okay, opposite and adjacent, that's tangent. So tangent of theta is equal to 2 over 3. So theta is equal to the inverse tangent of 2/3. Furthermore, we can say, oh, well, how long is this vector? We know it's 3, 2, but what's the actual length of the vector? To do that, we can do the Pythagorean theorem. We can say, well, this side, if we call it x, then x is equal to 3 squared plus 2 squared, all square rooted. So these give us general formulas for how to find the length and angle of a vector. So if we have a vector, which I will call A, again, the length of the vector is called its magnitude, and it's denoted by double bars on both sides. So this is equal to the square root of the x component squared plus the y component squared. This is really just the Pythagorean theorem in disguise. That's exactly what we did here. The x component squared plus the y component squared, and that's equal to the length of the vector. To find the angle the vector is at, the angle theta is just equal to the inverse tangent of a sub y over a sub x, right? This is our opposite, this is our adjacent. Opposite over adjacent is tangent. So to get the angle, we take the inverse, and we're all set. So that's what you're going to need to be able to do as your introductory things to how to manipulate vectors, how to break them into components, how to combine components. And we're going to see why this is useful in upcoming videos.